There's something hauntingly beautiful about the unknown, those corners of the universe where science meets mystery, where the rules we think we understand start to bend and blur. And few places in the cosmos embody that enigma more than the Leo cluster. Picture this, a sprawling gathering of galaxies, millions of light years across, where the fabric of reality seems to twist in ways that defy explanation. This isn't just another patch of space, it's a cosmic playground of the unexplained, where strange signals flicker, invisible forces tug at stars, and entire galaxies move in patterns that shouldn't be possible. What if I told you that some of the universe's most baffling secrets are hiding right there, in the heart of the Leo cluster? From ghostly radio emissions with no known source to galaxies that spin backward against the laws of physics, this region is packed with phenomena that leave even the brightest astronomers scratching their heads. And today, we're diving deep into 25 of these mind-bending mysteries, each one more perplexing than the last. Think of this as a cosmic detective story, where the clues are scattered across millions of light years, and the answers might just rewrite everything we thought we knew about the universe. But here's the thing, these aren't just abstract puzzles for scientists to solve. They're glimpses into the raw, untamed nature of reality itself. Every unexplained flicker, every gravitational anomaly, is a reminder that the universe is far stranger and more wondrous than we could ever imagine. So if you've ever stared up at the night sky and felt that tug of curiosity, that longing to unravel the secrets of the cosmos, then you're in the right place. Buckle up, because we're about to embark on a journey through the Leo cluster's greatest enigmas, and trust me, by the end, you'll never look at the stars the same way again. The first mystery we encounter in the Leo cluster is so bizarre it could be called a cosmic ghost story, the Phantom Galaxy. This isn't just a flickering speck in the night sky, it's an entire galaxy that plays an eerie game of hide and seek with astronomers. One moment, telescopes capture it clearly, its spiral arms stretching across the void. The next, it fades into near invisibility, as if someone flipped a switch. This isn't a trick of the light or faulty equipment, it's a real, repeatable phenomenon that defies everything we know about how galaxies behave. What makes this vanishing act even stranger is that the Phantom Galaxy doesn't follow the usual rules of dimming or brightening. Most galaxies change visibility predictably, dust clouds pass in front, or their stars flare and fade in patterns we understand. But this one disappears abruptly, sometimes for years at a stretch, then reappears just as suddenly. Some researchers suspect dark matter might be the culprit, warping the light around the galaxy like a cosmic funhouse mirror. Others speculate about exotic physics, perhaps pockets of unstable space-time, or even an unseen black hole acting like a cosmic dimmer switch. But here's the kicker, when the Phantom Galaxy is visible, it moves in ways that shouldn't be possible. Its stars orbit at speeds that our current models of gravity can't fully explain, as if some invisible hand is tugging them off course. This isn't just a puzzle, it's a direct challenge to our understanding of how galaxies form and evolve. If dark matter alone can't account for these wild inconsistencies, what else is out there bending the rules of the universe? Every time this galaxy winks back into view, it feels less like an anomaly and more like a taunt, a cosmic riddle waiting to be solved. The Phantom Galaxy forces us to ask uncomfortable questions. Are we missing something fundamental about the nature of matter? Could there be forces at work we haven't even discovered yet? Whatever the answer, one thing's certain, this ghostly enigma isn't just a fluke. It's a clue, one that might lead us to rewrite the textbooks on galactic evolution. And if something this strange can hide in plain sight, what else is lurking in the depths of the Leo cluster? If the Phantom Galaxy left you questioning reality, wait until you hear about the Leo cluster's most head-scratching paradox, the gravity anomaly. Nestled deep within this cosmic congregation is a region where gravity itself seems to have gone rogue. Here, the pull of invisible forces bends the paths of galaxies with no visible source, no dense clusters of stars, no looming black holes, just empty space acting like it's packed with phantom mass. This isn't just a minor discrepancy, it's a full-blown rebellion against Einstein's theory of general relativity, the very framework we've used to understand gravity for over a century. Imagine tossing a ball into the air, only for it to curve sideways instead of falling back down. That's the level of defiance we're seeing on a galactic scale. Galaxies in this zone race around their orbits faster than they should, as if whipped by some unseen cosmic lash. Scientists call this missing gravity, but the implications are anything but simple. Some argue it's evidence of dark matter clumping in ways we can't detect, while others whisper about something far more radical, flaws in Einstein's equations themselves. Here's where it gets even stranger. The anomaly's gravitational fingerprint doesn't match predictions for dark energy, the mysterious force accelerating the universe's expansion. Instead, it behaves like a localized glitch in spacetime, a pocket where the rules twist. One daring theory suggests exotic matter particles with negative mass might be warping gravity like a funhouse mirror. Others propose unseen dimensions leaking influence into our own. But the real shocker, this anomaly isn't alone. Similar pockets have cropped up in other clusters, hinting at a pattern. If gravity doesn't play by the rules here, what stops it from rewriting them everywhere? Every telescope trained on this region brings back more questions than answers, and that's what makes it thrilling. We're not just mapping the universe anymore, we're peering into its cracks where the next revolution in physics might be hiding. Just when we thought the Leo cluster couldn't get any stranger, we stumble upon a region so silent it's unsettling, the radio silence void. Imagine tuning an old-fashioned radio, twisting the dial through static and distant stations, only to hit a channel where nothing comes through. No hiss, no whispers from distant stars, just pure, unbroken silence. That's what astronomers found here, a vast expanse of space where even the cosmic background radiation, the faint echo of the Big Bang itself, seems to vanish. It's as if someone draped an invisible curtain across this patch of the universe, muffling every signal in its path. At first, researchers assumed it was a technical glitch. Maybe interference from Earth's atmosphere or a malfunction in the equipment. But after years of cross-checking with telescopes around the world, the silence held. This wasn't an error, it was a feature of the cosmos. The void spans hundreds of light years, a perfect bubble of radio quiet in a universe that's supposed to hum with energy. Even the emptiest corners of space still thrum with the faint glow of microwaves left over from the birth of the universe, but here, nothing. So what could possibly block all radio waves without a trace? One theory points to an exotic form of matter, a cosmic filter made of particles we've never detected, scattering or absorbing electromagnetic waves before they reach us. It's like trying to shine a flashlight through a wall of pure darkness. Another idea, far more speculative, suggests something deliberate, an alien megastructure designed to cloak or harvest energy. Picture a Dyson sphere, but on an unfathomable scale, built not around a star but an entire region of space. Far-fetched, maybe, but when natural explanations fall short, even the wildest possibilities demand consideration. Then there's the spacetime angle. Could this void be a rare pocket where the fabric of the universe is fundamentally different? Some theorists propose a cosmic defect, a kink in the dimensions we know where radio waves simply can't propagate. It's the equivalent of trying to shout underwater. The medium itself stifles the sound. If true, this wouldn't just be a curiosity. It'd be a window into physics beyond our current models, where the rules we take for granted don't apply. But here's what chills astronomers most. The silence isn't static. Over decades of observation, the void's edges have shifted subtly, as if it's breathing. Whether that's due to some natural cosmic process or something else entirely, no one can say. What we do know is that the radio silence void isn't just an absence, it's an active mystery. And in a universe that's never silent, the places that refuse to speak might have the most to tell us. Deep in the heart of the Leo cluster, a celestial lighthouse pulses erratically, a quasar that refuses to follow the script. Most quasars, those brilliant beacons powered by supermassive black holes, shine with a steady rhythm, their brightness fluctuating in predictable cycles. But this one, nicknamed the Flashing Quasar, behaves like a cosmic strobe light, erupting in violent bursts of energy without warning or pattern. One week it might remain eerily dim, the next it could outshine an entire galaxy for just a few hours before vanishing back into obscurity. These aren't gentle flickers, they're full-blown tantrums of radiation, blasting across the electromagnetic spectrum with enough force to scramble our instruments. What makes these flashes truly baffling is how they defy the standard model of quasars. Normally, as matter spirals into a black hole's accretion disk, it heats up and glows consistently like water circling a drain. But the flashing quasar's disk seems to be feeding in fits and starts, as if something keeps interrupting the flow. Some theorists suggest a second, smaller black hole might be orbiting the primary one, periodically disrupting the disk like a shark thrashing through a school of fish. Others propose the disk itself is warped, twisted by magnetic fields so intense they create bottlenecks, causing matter to pile up suddenly before bursting through in erratic surges. Then there's the timing. These flares don't just lack regularity, they defy statistical models altogether. Most cosmic phenomena, even the most violent, follow some underlying pattern, however complex. Supernovas, pulsars, even erratic blazars still fit within probabilistic frameworks, but the flashing quasar's outbursts appear genuinely random, like rolls of a cosmic dice. It's the difference between predicting a thunderstorm and trying to guess when a light bulb might explode. The implications reach far beyond this single anomaly. If black holes can switch their feeding modes this abruptly, it challenges our assumptions about how they influence galaxy evolution. Could similar quasars be masquerading as dormant in other clusters? Worse, what if we've been misjudging the activity of supermassive black holes entirely, mistaking their erratic pauses for permanent slumber? Every flash from this quasar isn't just a spectacle, it's a glimpse into the turbulent, unforgiving physics governing the most powerful objects in existence. And until we crack its code, we're left watching, waiting for the next unpredictable blaze to rewrite the rules once more. Hidden among the glittering tapestry of the Leo cluster, two celestial oddities lurk in plain sight: the twin dark stars. Unlike ordinary stars, these enigmas don't blaze with light or heat. They're invisible to telescopes, betraying their presence only by the way they twist the fabric of spacetime itself. Picture throwing a heavy ball onto a stretched sheet. The dent it creates warps the path of anything passing nearby. That's exactly how astronomers stumbled upon these shadowy giants, by watching distant galaxies behind them stretch and distort, as if seen through a funhouse mirror. What makes the twin dark stars so extraordinary isn't just their darkness, it's the sheer scale of their gravitational pull. Each one packs the mass of hundreds of suns into a space no larger than a solar system, bending light so fiercely that they act like cosmic magnifying glasses. Yet when scientists point infrared or X-ray detectors toward them, they find nothing. No radiation, no stellar winds, not even the faint glow of cooling matter. It's as if the universe carved out two bottomless pits where stars should be and left them humming with gravity alone. The leading theory: these might be the first confirmed examples of dark stars, hypothetical objects made not of atoms but of exotic particles that refuse to interact with light. Some researchers speculate they're built from actions, ghostly particles that barely acknowledge ordinary matter. Others wonder if they're clumps of primordial black holes, remnants of the universe's violent birth, somehow frozen in stasis. But here's the twist: their gravitational signatures don't quite match either scenario. They're too dense for black holes, yet too diffuse for most dark matter models. Then there's their dance. The twins orbit each other in a slow, precise waltz, their mutual tug creating ripples in spacetime that detectors can barely sense. If they were made of normal matter, their orbits would decay over time, but these two show no sign of slowing down. It's as if they're drawing energy from the vacuum of space itself, a feat that defies our understanding of thermodynamics. Every observation deepens the mystery. Are these relics of a stranger, earlier cosmos? Could they be doorways to something beyond our current physics? One thing's certain, in a universe where darkness usually means emptiness, the twin dark stars scream that sometimes the void has teeth, and whatever they are, they're rewriting the rules of what a star can or can't be. At the heart of the Leo cluster, astronomers have stumbled upon a cosmic contradiction, a monstrous tangle of galaxies so tightly packed it defies the universe's own blueprint. Dubbed the cosmic web knot, this dense galactic snarl shouldn't exist under our current understanding of cosmic evolution. Picture a spider's web, its delicate strands stretching across empty space, except here, one intersection is a tangled clump thicker than the rest of the web combined. Simulations predict matter should distribute evenly across the cosmos, forming a lace-like structure with gentle variations. But this knot, it's a cosmic traffic jam where dozens of galaxies crowd together like sardines, crammed into a space half the size they should occupy. What makes this knot so baffling isn't just its density, it's the way these galaxies move. Instead of drifting apart over billions of years, they seem locked in a gravitational embrace, as if some unseen hand stitched them together. Cosmologists have two leading explanations, and both rewrite pieces of cosmic history. The first points to primordial density fluctuations, ripples in the infant universe so extreme they left behind over-dense pockets where galaxies clustered abnormally. Think of it like a cake batter with one stubborn lump that refused to mix, preserving a relic of the universe's chaotic infancy, but the wilder theory. This knot might be a bruise from a collision with another universe. Some models of multiverse physics suggest neighboring universes could occasionally bump against ours, leaving behind imprints in the cosmic web. It's like finding a fingerprint on a window, evidence of something pressing in from the other side. While controversial, this idea gains traction from the knot's unusual radiation signature, faint, concentric ripples in the cosmic microwave background, as if spacetime itself bears the shockwaves of an ancient impact. Here's where it gets even stranger. The galaxies within the knot share chemical compositions unlike their neighbors' higher concentrations of heavy elements, as if they formed from a different recipe. Were they forged in a separate cosmic cauldron before being woven into our universe? Or does this suggest entire strands of the cosmic web might be alien in origin? Every new observation deepens the mystery, forcing scientists to confront an unsettling possibility. Our universe might not be the only one leaving fingerprints on the Leo cluster. And if that's true, this knot isn't just an anomaly, it's a cosmic handshake waiting to be decoded. Tucked away in the Leo cluster's swirling depths lies a nebula that doesn't just bend light, it twists time itself. The Time-Dilation Nebula is a cosmic hourglass where the universe's clock ticks slower, as if some invisible hand has pressed pause on reality. Picture an astronaut floating at its edge, watching their ship's instruments count seconds normally while their companion, drifting just a few kilometers deeper into the nebula's glow, moves in sluggish slow motion. Back on Earth, telescopes capture this surreal scene. Stars near the nebula's core pulsing lazily, their light stretched into deep reds, while those at the periphery shine bright and quick. This isn't an illusion, it's a real-world demonstration of Einstein's wildest predictions, playing out on a scale so vast it challenges our grasp of physics. What could warp time so dramatically? The answer lies in the nebula's heart, where gravity reaches nightmare intensities. Most nebulae are cosmic nurseries, clouds of gas and dust so diffuse you could fly through them without noticing. But this one harbors a secret, a hidden mass so dense it warps spacetime like a bowling ball on a trampoline. Einstein's theory of general relativity tells us that gravity doesn't just pull objects, it bends the very fabric of reality, slowing time where gravity is strongest. Near a black hole, this effect is extreme. Here, it's as if the nebula has trapped a black hole's gravitational fury without the hole itself. Spectrographs reveal no singularity, no event horizon, just a diffuse glow with the gravitational footprint of something far more sinister. Some theorists propose an exotic culprit, a gravitational condensate, a hypothetical soup of particles so massive they act like liquid spacetime, pooling gravitational energy without collapsing into a singularity. Imagine a whirlpool that never drains, spinning endlessly in the cosmic sink. Others suggest the nebula might be threaded with cosmic strings, filaments of primordial energy left over from the Big Bang, thinner than an atom but dense enough to knot spacetime around them. These strings, if they exist, could braid the nebula into a natural time machine, creating pockets where clocks tick at different rates, but the most unsettling possibility. This nebula might not be unique. If spacetime can fray so easily, forming accidental time warps in the cosmic wilderness, what does that mean for our understanding of the universe's flow? Could entire regions exist where time runs backward or loops on itself? Every flicker of light from the Time-Dilation Nebula carries a whisper from the future, or perhaps the past, reminding us that time is not the steady river we imagine, but a turbulent sea, full of hidden currents and uncharted whirlpools. And if Einstein's math holds true, the most mind-bending journeys through time might not require machines at all, just a voyage into the Leo cluster's heart. Among the countless galaxies swirling through the Leo cluster, one stands out not for its brilliance or size, but for its uncanny reflection. Astronomers call it the Mirror Galaxy, and it's as if the universe sketched the same cosmic blueprint twice. Light years apart, this galaxy and its apparent twin share spiral arms with identical kinks, dust lanes that curve in perfect synchrony, even star-forming regions that ignite in lockstep. The odds of two galaxies evolving this similarly by chance, astronomers put it somewhere between statistically ridiculous and flat-out impossible. So what's really going on here? One explanation points to gravitational lensing, the warping of light by massive objects, but there's a catch. For lensing to create such a precise mirror, you'd need an invisible colossal mass positioned just right between Earth and these galaxies, bending light like a funhouse mirror to project a flawless duplicate. Yet after scouring the region, telescopes found no such lens, no black hole, no dark matter clump, nothing dense enough to twist spacetime into a copy machine. That's where things get speculative. Could this be a glitch in the cosmic code? Some theorists suggest we're seeing a space-time echo, where the fabric of reality folds back on itself, replaying the same galactic formation process in two places at once. Others propose quantum entanglement scaled up to galactic proportions, though how particles light years apart could influence entire galaxies remains a mystery wrapped in enigma. Then there's the multiverse angle. If parallel universes exist, their gravity might occasionally bleed through, imprinting duplicate structures in our own cosmos. Picture soap bubbles bumping together, transferring patterns across their surfaces. Far-fetched, maybe, but when conventional physics falls short, even the wildest ideas deserve a seat at the table. Whatever the truth, the Mirror Galaxy forces us to confront a humbling possibility. The universe might be more interconnected or more convoluted than we ever imagined. And if one cosmic reflection exists, how many others have we missed? Most black holes anchor their galaxies like cosmic puppeteers, their immense gravity dictating the dance of stars around them. But deep in the Leo cluster, one has gone rogue, a supermassive fugitive barreling through intergalactic space without a galaxy to call home. This isn't just unusual, it's like finding a skyscraper adrift in the ocean, unmoored from any city. The Unbound Black Hole weighs in at several million solar masses, yet it travels alone, leaving no trace of the stellar metropolis it once ruled. How does something so monstrous break free? The leading theory involves a cosmic demolition derby, a violent collision between galaxies that sent this black hole careening into the void. When galaxies merge, their central black holes eventually spiral together. But if a third galaxy disrupts their dance, the chaotic gravitational kick can fling one out entirely. Picture a game of celestial billiards where the cue ball is a black hole traveling fast enough to cross the distance between Earth and the Moon in minutes. That's the kind of energy needed to unbind something this massive. Yet this explanation raises fresh mysteries. The black hole's trajectory shows no obvious path back to a parent galaxy, and its speed is oddly constant, as if propelled by some unseen force. Some researchers suggest it might be trailing dark matter filaments, invisible cosmic ropes tugging it along. Others wonder if it was never bound to a galaxy at all, but formed in the early universe from a direct collapse of primordial gas, a relic from before galaxies even existed. What's truly unsettling, though, is the wake it leaves behind. As the black hole plows through intergalactic gas, it generates shockwaves that glow in X-rays, a ghostly breadcrumb trail of its passage. But these emissions flicker unpredictably, hinting at sporadic feeding frenzies where it devours stray gas clouds. Could there be others like it, drifting unseen? If so, they'd rewrite our understanding of how black holes form and wander through the cosmos. The Unbound Black Hole forces us to confront an eerie truth. The universe might be teeming with runaway giants, dark nomads roaming the voids between galaxies. And if one could escape its galactic chains, what's stopping others from doing the same? Every new observation of this cosmic renegade chips away at our assumptions, reminding us that even the most fundamental rules of astrophysics might have exceptions lurking in the shadows of the Leo cluster. Most gamma-ray bursts light up the cosmos like cosmic flashbulbs, violent explosions that leave behind lingering afterglows of X-rays and visible light, clues for astronomers to decode their origins. But the Leo cluster holds two exceptions to this rule: bursts of gamma radiation so intense they should have scorched the sky, yet when scientists turned their telescopes to pinpoint the aftermath, they found nothing. No glowing debris, no fading heat signature, just empty space where a cataclysm should have been. These aren't just mysterious, they're cosmic magic tricks where the universe whispers, "Now you see it," before snuffing out the evidence entirely. The first of these ghostly bursts, dubbed Phantom Flash, lasted less than 2 seconds but packed enough energy to outshine a supernova. Gamma-ray telescopes caught its lethal spark, a pulse so bright it briefly drowned out nearby galaxies. Yet follow-up observations revealed no neutron star collision, no black hole birth, not even a wisp of heated gas. It's as if the universe detonated a firework in a soundproof room, leaving no trace of the blast. The second event, Spectre Surge, was even stranger. A millisecond flicker of gamma rays followed by a peculiar radio whisper, a signal that faded within hours. Neither fit the profile of known cosmic explosions, leaving theorists scrambling for explanations. One possibility: failed supernova, stars that collapse inward so completely they vanish without the usual fireworks. Imagine a dying star's core imploding directly into a black hole, swallowing its own death cry before light can escape. It's the astrophysical equivalent of a building demolishing itself into a sinkhole, leaving no rubble behind. Yet even this theory stumbles. These bursts were too energetic for typical stellar collapses, their gamma-ray signatures oddly clean, lacking the messy afterglow of disintegrating matter. Then there's the neutron star angle. When these ultra-dense stellar corpses collide, they often produce short gamma-ray bursts and gravitational waves. But mergers leave behind telltale debris, a kilonova's radioactive glow, or a newborn black hole's accretion disk. Here, silence, unless, of course, the remnants were ejected at near light speed, vanishing beyond detection before telescopes could swing into action. Some speculate these bursts might be naked mergers, events where the collision's energy jets punch straight through spacetime, leaving no sideways radiation for us to detect. But let's address the elephant in the cosmos. Could these be artificial? The idea isn't as outlandish as it sounds. A sufficiently advanced civilization might harness gamma rays for propulsion or communication, creating directed beams visible across the universe. Phantom flashes' brevity and purity mirror what theorists predict for an engineered signal: brief, intense, and intentionally fleeting to avoid detection. Spectre surges paired radio blip adds fuel to the fire. Why would a natural event produce two distinct emissions unless it was designed to? Skeptics counter that nature is stranger than fiction, and human bias often paints unknowns as alien prematurely. Still, the possibility lingers, a tantalizing what if, in an era where humanity actively hunts for extraterrestrial technosignatures. What makes these bursts truly unsettling is their implication. If colossal cosmic explosions can vanish without a trace, how many others have we missed? Are these rare flukes or the first hints of a hidden population of stealth gamma-ray events flickering at the edge of detectability? Every time a new burst lights up the Leo cluster, astronomers hold their breath, waiting to see if this one too will dissolve into the dark, taking its secrets with it. There's a star in the Leo cluster that shouldn't exist, not because it's too bright or too massive, but because it's too cold. Meet the frozen star, a celestial paradox burning a hole in our understanding of stellar physics. While most stars scorch their surfaces at thousands of degrees, this one lingers just a whisper above absolute zero, the theoretical floor of temperature where all motion stops. At -273.15 degrees Celsius, it's colder than the void between galaxies, colder even than the afterglow of the Big Bang itself. If you could touch it, your hand would freeze faster than if you dipped it into liquid nitrogen. So how does a star, a cosmic engine powered by nuclear fusion, end up colder than deep space? The answer isn't just elusive, it's rewriting the textbooks. Normally, stars like our Sun blaze for billions of years before exhausting their fuel and shrinking into white dwarfs, dense embers that glow faintly with leftover heat. But the frozen star defies this script. Spectrographs reveal it isn't a white dwarf. Its composition is all wrong, lacking the expected heavy elements like carbon and oxygen. Instead, it's a bizarre cocktail of light gases, as if someone siphoned off a star's outer layers and left behind a frozen, inert core. One theory suggests it might be a failed star, an object too puny to ignite fusion in the first place. Brown dwarfs, the so-called star-planet hybrids, fit this mold, but even they radiate warmth from gravitational contraction. The frozen star, though, shows no such heat signature. It's as if it formed cold and stayed that way, a cosmic stillbirth lingering in the stellar graveyard. Then there's the quantum angle. Some researchers speculate this could be a quark star, an exotic remnant where matter crushes down into fundamental particles, creating a super-dense, super-cold object. Under enough pressure, protons and neutrons might dissolve into a soup of quarks, releasing energy in ways that don't produce heat. Picture an ice cube that never melts because its atoms are locked in a quantum deep freeze. But the most tantalizing possibility, the frozen star might be a relic from a previous cosmic cycle, a survivor from a universe before ours where the laws of physics were subtly different. If matter behaved oddly under those ancient rules, it could explain why this object refuses to play by our universe's thermodynamic playbook. Every observation deepens the chill of this mystery, leaving astronomers to wonder, is this a fluke or a signpost to an entirely new branch of stellar evolution? One thing's certain: wherever the frozen star came from, it's proof that the universe still has secrets colder than the void itself. Imagine a world where the ground beneath your feet isn't rock or ice, but a single, shimmering sheet of diamond. In the Leo cluster, that's not science fiction, it's reality. Astronomers have dubbed it the Diamond Planet, a celestial jewel forged under conditions so extreme they make Earth's deepest diamond mines look like sandboxes. This planet's surface isn't just scattered with gemstones. It's likely one colossal, crystalline structure, a crust of carbon compressed into perfect lattices over billions of years. How does something this extravagant form? The answer lies in stellar alchemy. Most carbon-rich planets start as remnants of dead stars, white dwarfs that once burned hot before shedding their outer layers, leaving behind cores dense with carbon and oxygen. But the diamond planet's origin story is even more dramatic. It orbits a pulsar, a rapidly spinning neutron star that bathes its companion in relentless radiation. Scientists believe this world was once a gas giant, its atmosphere stripped away by the pulsar's fury, leaving behind a bare core of carbon subjected to crushing pressures. Over eons, those conditions transformed the carbon into diamond, like a cosmic blacksmith hammering coal into a flawless jewel. Yet the real mystery isn't just how it formed, but why it survived. Diamond is brittle, a single strike can shatter it. So how does this planet endure the pulsar's gravitational tides without crumbling? Some models suggest its diamond crust might be laced with metallic veins, a natural alloy flexing under stress. Others propose it's wrapped in a thin, superheated atmosphere of ionized carbon, acting like a shock absorber against stellar turbulence. Then there's the bigger question: is this planet unique? Carbon worlds are rare. Most planets form from silicate-rich material like Earth. But if the Leo cluster hosts even one, others might lurk in similar extreme environments. Could entire systems of diamond planets exist, forged in the wake of supernova or pulsar collisions? Every scan of this glittering anomaly brings us closer to an unsettling truth. The universe might be far richer and far stranger than our periodic tables suggest. What would it be like to stand on such a world? Picture a landscape of fractured light, where the horizon gleams like a mirage and the sky pulses with the deadly rhythm of a neutron star. But here's the cruel twist: that dazzling surface would be a death trap. Diamond conducts heat poorly, meaning the planet's interior could be a furnace trapped under an icy shell, a pressure cooker waiting to erupt. One crack and pent-up gases might explode, scattering diamond shards into space like cosmic confetti. The diamond planet isn't just a curiosity, it's a challenge. It forces us to rethink how planets evolve under extreme conditions, and whether rarity is the exception or the rule. And if whole worlds can crystallize into gems, what other impossible wonders are waiting in the dark? In the quiet depths of the Leo cluster, a patch of space flickers with something impossible: quantum mechanics writ large, playing out on a stage meant for stars. This is the quantum ripple, a region where the tiny, probabilistic jitters of particles normally hidden within atoms stretch across light years, tugging at entire star systems like invisible marionette strings. Imagine throwing a pebble into a pond and watching the ripples distort not just the water, but the trees on the shore. That's the level of defiance happening here, quantum uncertainty scaling up to warp the cosmos itself. The phenomenon centers on a group of stars whose orbits shudder unpredictably, as if buffeted by unseen waves. Traditional gravity can't explain these tremors. They're too fine, too rapid, matching none of the usual suspects like hidden planets or passing dark matter. Instead, the star's movements mirror the behavior of particles in a quantum superposition, existing in multiple states until measured. But here's the catch: superposition should collapse at macroscopic scales. A star can't be in two places at once unless the rules are breaking down. Theorists are scrambling. One camp argues this could be the first evidence of quantum gravity, a missing link between Einstein's relativity and the quantum world. Perhaps spacetime itself is pixelated at microscopic levels, And in this region, those pixels have glitched, letting quantum effects leak into the classical realm. Picture a digital screen zoomed in until you see the individual pixels, then realizing some are stuck between colors. Another faction suggests a more radical idea, that the stars aren't being influenced by quantum effects, but are made of something never before seen, quantum degenerate matter, a phase where macroscopic objects behave like entangled particles. Then there's the observational oddity. The ripple's influence isn't uniform. It pulses in cycles, growing stronger when aligned with certain cosmic background radiation frequencies. It's as if the universe itself is tuning the phenomenon, turning the volume up and down on reality's quantum static. Could this be a natural amplifier for effects we've always missed? Or is it a temporary fissure in the fabric of physics, soon to snap shut? What makes the quantum ripple so unnerving isn't just its existence, it's the precedent. If quantum fluctuations can sway stars here, why not elsewhere? Are we seeing a rare fluke or the tip of an iceberg? Every telescope trained on this anomaly risks revealing something even more startling, that the boundary between the quantum and classical worlds isn't a fixed wall but a fraying curtain. And behind it, the universe might be far stranger than we ever dared to dream. Even in a cluster brimming with cosmic oddities, few things unsettle astronomers like objects that refuse to stay put, or worse, refuse to stay visible. Case in point, the vanishing moons, two celestial bodies locked in orbit around a turbulent gas giant in the Leo cluster, flickering in and out of existence like glitches in reality itself. One moment, telescopes capture them clearly rocky spheres pockmarked with craters, their surfaces reflecting the dull glow of their parent planet. The next, they're gone, leaving behind empty space where satellites should be. These aren't mere eclipses or shadows. These disappearances last for days, sometimes weeks, before the moons abruptly rematerialize as if nothing happened. The first mystery is the sheer inconsistency. Most cosmic vanishing acts like asteroids obscured by dust or planets hidden behind stellar flares follow predictable patterns. But these moons vanish at irregular intervals with no correlation to their orbital positions or external interference. Even stranger, when they reappear, their trajectories sometimes show subtle shifts as if they've been nudged by an unseen force. One theory points to cloaking technology not from aliens but from nature itself. Certain exotic materials, like metamaterials with negative refractive indices, could bend light around an object, rendering it invisible. If these moons harbor caves or crusts laced with such substances, perhaps tidal forces from their gas giant temporarily activate them, like a cosmic light switch flipping on and off. Then there's the dimensional rift hypothesis. Some physicists speculate the moons might be straddling a flaw in spacetime, a place where our universe brushes against another. Picture a sheet of paper with two dots drawn close to a fold. When the paper bends, the dots touch. When it flattens, they separate. If these moons sit at such a kink, they could be slipping in and out of our dimension, vanishing when the fold shifts. Supporting this idea are fleeting gravitational anomalies detected during the disappearances, tiny spikes in spacetime curvature that hint at something massive passing through our universe without fully entering it. Of course, skeptics argue for simpler explanations, observational errors perhaps caused by interstellar plasma distorting radio signals, or temporary obscuration by clouds of debris ejected from the gas giant. Yet no known debris field matches the timing or scale of these events, and the moon's reappearances are too precise to blame on static. Even more confounding, spectral analysis reveals their composition changes slightly after each disappearance. Minerals absent before suddenly appear, as if the moons are being subtly altered during their time away. What if the truth lies beyond our current physics? Quantum mechanics allows for particles to tunnel across barriers. Could entire moons be tunneling elsewhere? Or are we seeing evidence of a universe where objects don't just move through space, but flicker in and out of existence as part of their natural state? Every time these moons return, they bring more questions than answers, a reminder that even the most familiar cosmic dance might have steps we've yet to learn. And if moons can vanish without warning, what else in the night sky might be hiding in plain sight? Somewhere in the Leo cluster, a dead star sings, not metaphorically, but literally broadcasting rhythmic radio pulses so precise they resemble structured musical notes. The singing pulsar defies the usual erratic chirps and static of its kind, emitting frequencies that rise and fall in sequences akin to scales, as if someone or something is tuning a cosmic instrument. Most pulsars stutter like misfiring engines, their beats irregular and chaotic. This one, it hums with eerie consistency, its radio waves cascading in patterns that mirror mathematical harmonics found in human compositions. So what's orchestrating this celestial melody? The leading theory points to magnetovibrations, neutron stars with crusts so dense they crack under magnetic pressure, creating seismic ripples that modulate their emissions like a drumhead vibrating after a strike. Picture plucking a guitar string. The pitch depends on tension and length. Similarly, the pulsar's superfluid interior might slosh against its rigid crust, generating oscillations that translate into radio notes. Supporting this, telescopes detected micro-glitches in the star's spin, tiny hiccups consistent with crustal fractures. But here's where skeptics raise eyebrows. The patterns aren't just orderly, they occasionally repeat in sequences resembling prime numbers, a hallmark some argue is too convenient for natural processes. Prime sequences are rare in nature but favored in hypothetical alien messaging systems because they're mathematically distinct from background noise. Could this be a lighthouse deliberately designed to catch our attention? The scientific community is divided. One faction insists it's pareidolia, our brains imposing meaning on randomness, like hearing words in white noise. Others counter that the pulsar's harmonics persist across multiple observations, resisting statistical dismissal. Then there's the tempo anomaly. Over decades, the pulsar's songs have subtly slowed, as if running out of breath. Natural spin down would gradually drain its rotational energy, but the decay in musical coherence is oddly linear, like a metronome winding down predictably. Unnatural, not necessarily dying stars often exhibit predictable cooling, but the precision unnerves even seasoned astronomers. Perhaps the most haunting possibility isn't that the singing pulsar is a message but a monument. Advanced civilizations might encode information in stellar objects as time capsules, knowing pulsars outlive biological life by eons. Or maybe we're hearing the death throes of a star uniquely sculpted by physics we've yet to grasp. Every pulse is a reminder the universe doesn't just move, it may also, in its own way, sing. And if one star can harmonize with the void, what other symphonies are echoing unseen? In the vast expanse of the Leo cluster, death usually comes with fireworks, supernovas so bright they outshine entire galaxies, painting the cosmos in brilliant hues of gold and blue. But one stellar demise broke the mold entirely. The lightless supernova didn't just defy expectations, it rewrote the rules of how stars die. When this cosmic titan reached the end of its life, it collapsed in utter silence, unleashing a cataclysm so dark telescopes caught nothing. No blinding flash, no radiant shockwave, just the eerie whisper of spacetime itself recoiling from the violence. At first, astronomers thought their instruments had failed. How could a supernova, the universe's most energetic explosion, leave no trace in visible light? The answer came from an unexpected corner of physics: gravitational waves. Detectors on Earth picked up ripples in the fabric of reality, distortions so intense they could only mean one thing: a massive object had imploded. Yet when scientists raced to pinpoint the source, they found no afterglow, no expanding debris cloud, just an empty patch of sky humming with gravitational aftershocks. It was like hearing the thunderclap of an unseen storm, a tempest that left no rain. The leading theory: this might have been the collision of two dark stellar corpses, objects so dense and strange they emit no light at all. Picture two black holes or neutron stars, their surfaces cloaked in exotic matter, slamming together with enough force to warp spacetime but without the fiery farewell of normal stars. Alternatively, the supernova's light could have been swallowed by something even more bizarre, a dark matter envelope, a shroud of invisible particles so thick it absorbed every photon before it could escape. Imagine setting off a bomb inside a pitch-black vault. The explosion happens, but no one outside ever sees the flash. Then there's the wild-card scenario. What if the star itself was made of dark matter? While most stars fuse hydrogen into helium, a dark star would be powered by the annihilation of weakly interacting particles, burning without the usual blaze of nuclear fusion. When such a star dies, its collapse might release energy in forms we can't see: gravitational waves, neutrinos, or even ripples in quantum fields we've yet to discover. The implications are staggering. If stars can die in darkness, how many supernovas have we missed? Could entire chapters of stellar evolution be hidden in the shadows, playing out in wavelengths we're blind to? Every time we train our telescopes on the lightless supernova's coordinates, we're met with the same unsettling silence, a reminder that the universe's grandest explosions might be the ones we never see coming. Amid the chaos of colliding galaxies and swirling nebulae, the Leo cluster holds an elegant oddity, a perfect spiral floating in empty space, as if someone carved a cosmic pinwheel into the fabric of reality itself. The celestial spiral isn't just beautiful, it's baffling. Unlike the messy, star-studded arms of spiral galaxies, this structure is pristine, its curves mathematically flawless, stretching hundreds of light-years across with no central engine to anchor it. No stars, no black hole, just an ethereal twist of glowing plasma suspended in the void like a silent whirlpool. How does nature craft something so unnervingly precise? The leading theory points to plasma filaments, superheated tendrils of ionized gas caught in a magnetic dance. When charged particles spiral along magnetic field lines, they can create intricate shapes, much like iron filings aligning around a magnet. But the celestial spiral's symmetry pushes this idea to its limits. Natural plasma formations tend to fray and kink, their structures dictated by chaotic forces. This spiral, though, looks sculpted, its curves too uniform, its geometry too deliberate. It's the difference between a flickering candle flame and a laser-cut glass ornament. Then there's the speculative camp, those who wonder if we're staring at something more than physics. Could this be a kind of cosmic art, an intentional marker left by an ancient civilization? Imagine a species so advanced they shape plasma like clay, twisting it into a beacon visible across the eons. Or perhaps it's the residue of a wormhole, a Chinese letter in spacetime where two universes briefly touched, leaving behind a gravitational fingerprint. Wormholes are theorized to produce spiral distortions as they stabilize, like water spiraling down a drain. If one formed and collapsed here, the celestial spiral might be its final frozen echo. But here's where the mystery deepens. The spiral emits a faint, anomalous radio signal, not random noise, but a repeating pulse buried in the static. Some researchers argue it's the hum of charged particles accelerating along the structure's arms, a natural byproduct of its magnetic fields. Others detect a pattern in the pulses, a sequence that mirrors prime numbers, a hallmark often cited in debates about artificial signals. Skeptics counter that nature loves patterns too, from the fractal branching of lightning to the Fibonacci spirals in sunflowers. Yet the question lingers, if this were a message, how would we even begin to decode it? The celestial spiral forces us to confront a fundamental tension in astronomy, the line between the awe-inspiring and the inexplicable. Is it a masterpiece of plasma physics, a fluke of magnetism pushed to its artistic extreme? Or is it a signpost, a deliberate stroke in the canvas of the cosmos, waiting for us to understand its language? Every time we observe it, we're left with the same humbling thought. the universe doesn't just create chaos. Sometimes, against all odds, it creates perfect order, and we still don't know why. Among the countless mysteries of the Leo cluster, few are as visually striking or as scientifically perplexing as the twin void bubbles. Picture two perfect spheres of nothingness, each spanning hundreds of light years, where galaxies and gas clouds refuse to enter, as if an invisible force field guards their boundaries. These aren't just empty regions, they're cosmic dead zones where matter behaves like opposing magnets, repelled by something we can't see. Astronomers first noticed them when mapping the cluster's structure, two eerie gaps in the celestial tapestry, too symmetrical and isolated to be random. What could carve such pristine voids in a universe where matter clumps together like cosmic glue? The first theory sounds like something from a science experiment gone wrong: antimatter explosions. When matter and antimatter collide, they annihilate in bursts of pure energy, leaving behind empty space. If pockets of antimatter survived the early universe, they might have detonated long ago, blasting away all surrounding material. The problem: we've never found evidence of natural antimatter reservoirs on this scale. Worse, annihilation would have left telltale gamma-ray signatures, radiation that's conspicuously absent here. Unless, of course, the explosions happened so long ago that their light has faded beyond detection, leaving only these ghostly craters as evidence. Then there's the far stranger possibility: dimensional portals. Some models of string theory suggest our universe could be pressed against others in higher dimensions, like pages in a book. Where these brains touch, they might form bridges, wormholes, or gateways to other realities. The twin void's flawless geometry fits this idea eerily well, as if they're cosmic portholes where matter drains into another plane of existence. Supporters point to subtle gravitational anomalies at the bubble's edges, ripples in spacetime that don't match the pull of visible matter. Could these be the gravitational echoes of something else tugging from the other side? But here's where it gets truly mind-bending. Recent observations show the voids aren't static. They're slowly drifting against the cluster's motion, like boats rowing upstream. If they were mere scars from ancient explosions, they'd move with the surrounding galaxies. This odd behavior has sparked yet another theory, that the voids are dark energy vacuoles, regions where the mysterious force accelerating the universe's expansion has pooled locally, pushing matter outward like cosmic repulsor fields. Whatever the truth, the twin void bubbles force us to confront an unsettling gap in our knowledge. Are they fossils of the universe's most violent moments? Windows to other dimensions, or something we haven't even imagined yet? Every new observation deepens the mystery, proving once again that in the Leo cluster, even the emptiest places hold the deepest secrets. In a corner of the Leo cluster where stars are born and die by the billions, one ancient beacon refuses to fade: the immortal star, a celestial Methuselah that's been shining for nearly twice as long as the universe says it should. Most stars its size should have burned out eons ago, collapsing into white dwarfs or exploding in supernova. Yet here it glows, defiantly stable, as if time itself has forgotten to claim it. This isn't just a cosmic outlier, it's a direct challenge to everything we know about stellar life cycles. What's keeping this star alive? One theory points to its core, where exotic matter might be rewriting the rules of fusion. Normal stars fuse hydrogen into helium, a process that eventually exhausts their fuel. But if the immortal star's heart contains strange quark matter, a hypothetical state where particles dissolve into a soup of fundamental components, it could be burning energy in ways we've never witnessed. Picture a candle that doesn't melt its wax but instead draws heat from some hidden reservoir beneath the table. The star's unusual neutrino emissions, detected by deep space observatories, hint at reactions far stranger than standard fusion, as if its core is tapping into a physics we've yet to discover. Then there's the external energy hypothesis. Some researchers suggest the star might be feeding off its surroundings, siphoning dark matter or interstellar plasma like a cosmic vampire. Dark matter, though invisible, could interact gravitationally, providing just enough extra mass to sustain fusion longer than expected. Alternatively, the star could be threading a dense filament of cosmic gas, drawing material in steadily to replenish what it burns. But here's the catch. Telescopes find no obvious accretion disk or gas streams nearby, leaving this theory on shaky ground. The wildest possibility: this star isn't a natural object at all. Advanced civilizations, if they exist, might engineer stellar life support systems, using technology to prolong a star's lifespan as an energy source or even a monument. While this idea strays into speculation, it raises a provocative question. In a universe teeming with wonders, how would we recognize something that wasn't just rare but deliberately made? Yet the immortal star's greatest lesson might be humility. Its existence forces us to admit that stellar evolution isn't as settled as we thought. If one star can cheat death, how many others have we misclassified? Every flicker of light from this ancient beacon isn't just a glow, it's a whisper from the cosmos, reminding us that some rules are meant to be broken. Gravity is supposed to be the universe's most reliable artist, always bending light with predictable precision, like a master glassblower shaping a flawless lens. But in the Leo cluster, there's a gravitational lens that can't seem to make up its mind. One moment, it magnifies distant galaxies with crystal clarity. The next, it distorts them into funhouse mirror absurdities, as if space-time itself has developed a nervous twitch. This isn't just imperfect optics, it's a full-blown gravity lens paradox, where the cosmos's most dependable tool suddenly forgets how to work. What makes this lens so baffling isn't just its inconsistency, it's the sheer unpredictability. Normally, gravitational lensing follows a strict script. Massive objects warp spacetime, bending light around them in smooth arcs. The more mass, the stronger the distortion. But here, galaxies behind the lens flicker between extreme magnification and near invisibility, like a telescope with a broken focus knob. Even stranger, the distortions don't always align with the visible mass in the foreground. It's as if the lens is being tugged by invisible fingers, adjusting its grip on light at random. Could dark matter be the culprit? Most models assume it's spread uniformly around galaxy clusters like an invisible fog. But if it's clumped unpredictably, piling into dense knots in some areas and thinning to near nothing in others, that might explain the lens's erratic behavior. Picture a pane of glass with hidden bubbles and warps. Light passing through would scatter chaotically. Yet even this theory stumbles. Detailed dark matter maps of the region show no obvious voids or clumps to justify the lens's wildest swings. Unless, of course, dark matter isn't just clumpy, it's somehow dynamic, shifting density like sand in an hourglass. Then there's the radical alternative. Maybe our understanding of lensing itself is flawed. Einstein's equations have passed every test for over a century, but what if extreme environments, like the heart of a chaotic galaxy cluster, reveal cracks in the framework? Some theorists propose modified gravity models, where the strength of spacetime's curvature isn't constant but depends on scale or energy. It's the difference between assuming a rubber sheet stretches evenly and discovering it's actually patchwork, some areas stiff, others oddly elastic. If true, this lens might be the first hint of a deeper truth, that gravity, like light, can come in shades we've yet to measure. The paradox takes a stranger turn when you consider timing. The lens's fluctuations aren't random noise, they follow a rough cycle with distortions peaking every few months. That's far too slow for stellar motions but too fast for typical dark matter drift. One speculative idea involves quantum foam, the hypothetical graininess of spacetime at microscopic scales. If these tiny fluctuations sometimes bubble up into macroscopic effects, they might tweak the lens's behavior like static distorting a radio signal. But here's the real kicker. Some magnified galaxies appear younger than they should. Light from distant objects takes billions of years to reach us, so we're seeing them as they were in the past. Yet a handful of lensed galaxies in this region show star formation rates that defy cosmic timelines, as if the lens isn't just bending light but tampering with time. Could this be a sign of localized time dilation, where spacetime's wrinkles run so deep they alter our view of cosmic history? Or is it evidence of something even weirder, like light taking multiple paths through warped dimensions, arriving out of sequence? The gravity lens paradox does more than challenge theories. It confronts us with the limits of our cosmic vision. If something as fundamental as lensing can't be trusted, how do we know what's real and what's a trick of the light? Every flicker of this capricious lens is a reminder: the universe doesn't owe us consistency, and sometimes the most revealing truths come from the places where the rules break down. The final enigma lurking in the Leo cluster isn't just strange, it's patient. Dubbed the cosmic echo, this signal arrives like clockwork every 10 years, pulsing across the void with eerie precision. But here's what chills astronomers to the bone: each repetition isn't an exact copy. The frequencies shift subtly, the intervals between pulses stretch or compress by milliseconds, as if whatever's sending it is learning, adapting, or perhaps counting down to something. At first glance, it resembles a pulsar's steady heartbeat, except pulsars don't evolve their rhythms over human timescales. Their spins slow predictably as they bleed energy, like a top winding down. The echo's changes, though, are deliberate, almost methodical. One theory suggests precession: a wobble in the star's rotation axis could alter the signal's timing. Imagine a spinning top tracing slow circles as it tips. A pulsar's beam might sweep past Earth at slightly different intervals, but to explain the echo's decade-long cycle, you'd need a wobble so precise it borders on the impossible. Then there's the pattern's complexity. Natural cosmic signals tend to be noisy, layered with static from magnetic fields or plasma turbulence. The echo, though, is startlingly clean, its modulation crisp enough to carry information. Some researchers argue this points to a maser, a natural laser-like amplification of radio waves by interstellar gas clouds. Yet masers are chaotic, their output sculpted by the whims of molecular chaos. The echo's variations, by contrast, follow mathematical progressions that hint at structure, not randomness, and that's where the speculation ignites. Could this be a message intentionally crafted to evolve? If so, its designers operate on timescales beyond human imagination, content to wait centuries for a reply. Perhaps each transmission is a chapter in a story, a cosmic hello growing more nuanced with each repeat. Or worse, a warning: its shifts encoding a countdown we've yet to decipher. Yet the most unsettling possibility isn't artificiality, but antiquity. The echo might be a fossilized ripple from an event long past. A black hole merges gravitational waves rebounding through space-time, or light trapped in a celestial hall of mirrors, echoing back to us with slight red shifts each round trip. If so, we're not hearing a sender at all, but the universe itself, replaying its own history in a loop we're only now learning to hear. Every decade, as the next echo arrives, telescopes worldwide train on the Leo cluster, searching for clues in its shimmering variations. But the real mystery isn't just what the signal says, it's whether anyone or anything is listening for our reply. The cosmic echo's pattern isn't just strange, it's mathematically elegant, a sequence so precise it feels almost intentional. Every 10 years, like clockwork, the signal pulses across the cosmos, but what's truly unnerving is how it evolves. Each repetition carries subtle shifts, frequencies sliding up or down the spectrum, intervals between pulses stretching or contracting by mere milliseconds. At first glance, it might seem random, but crunch the numbers and a chilling pattern emerges. The changes follow a logarithmic progression, a curve so smooth it mirrors the countdown timers used in human spacecraft. It's as if the universe itself is ticking away the seconds, but to what end? One theory suggests the echo could be a natural oscillator, a celestial object trapped in a feedback loop. Picture a star trapped in a gravitational dance with an invisible partner. A black hole, perhaps its orbit decaying incrementally with each pass, subtly altering the timing of its radio whispers. But here's the catch: the precision of the decay doesn't match any known astrophysical process. Stars in death spirals don't slow down this predictably. Their orbits fray chaotically as they're torn apart. The echo's rhythm, though, is algorithmic, its adjustments following a near-perfect exponential function. It's the difference between a dying engine sputtering to a halt and a metronome set by a mathematician. Then there's the signal structure. Most cosmic radio emissions are messy, a cacophony of static and interference. The echo, by contrast, is eerily clean, its pulses shaped like sine waves, the purest form of mathematical vibration. This level of coherence is rare in nature. Even pulsars, the universe's most precise timekeepers, show slight jitters in their beats caused by crustquakes or magnetic storms. The echo's signal, though, is pristine, as if filtered through some cosmic amplifier that strips away all noise. Some researchers argue this points to a maser mechanism, a natural laser effect where interstellar gas clouds focus radio waves into sharp beams. Yet masers are inherently chaotic, their output sculpted by turbulent molecular clouds. The echo's clarity suggests something far more controlled. This leads to the inevitable, spine-tingling question: could the echo be engineered? The logarithmic progression, the signal's purity, even the 10-year cadence, all hint at design. Human spacecraft use similar countdown protocols in telemetry, adjusting transmission intervals as missions progress. If this is a message, its creators think on timescales beyond our comprehension, content to wait centuries between exchanges. The signal's gradual shifts might encode information, each tweak a syllable in a sentence stretched over millennia. Alternatively, it could be a distress beacon, a cosmic SOS broadcast by a civilization facing extinction, its final plea repeating long after its senders are gone. Yet the most profound possibility isn't artificiality but antiquity. The echo might be a relic of the early universe, a ripple frozen in time. Imagine a black hole collision so violent it sent gravitational waves ringing through spacetime like a struck bell. Those waves could have bounced off hidden dimensions or cosmic defects, returning to us as faint echoes, their intervals stretched by the universe's expansion. Each return would carry a slightly slower tempo, a natural redshift etched into the pattern. If true, the echo isn't a signal at all, it's the universe replaying its own birth pangs, a whisper from the dawn of time. Whatever the truth, the cosmic echo defies easy explanation. It's a riddle wrapped in mathematics, a pulse that feels both ancient and alive. Every decade, as telescopes strain to catch its next whisper, we're left wondering, are we listening to the universe's heartbeat, or the last gasp of something, or someone trying to be heard? The cosmic echo doesn't just baffle astronomers, it forces us to confront one of the most haunting questions in science. If the universe is so vast and ancient, why does it feel so empty? This is the heart of the Fermi paradox, the glaring contradiction between the high probability of extraterrestrial civilizations and the utter silence that greets our searches. The echo, with its eerie precision and cryptic evolution, epitomizes that paradox. Here we have a signal sophisticated enough to hint at intelligence, yet no sender steps forward to claim it. No empires announce themselves, no beacons broadcast greetings, just this solitary pulse, repeating across the eons like a message in a bottle washed ashore with no return address. Consider the numbers. The Leo cluster alone contains thousands of galaxies, each brimming with billions of stars. Even if only a fraction of those stars host habitable planets, the statistics suggest civilizations should be commonplace. So where is everyone? The echo's existence deepens the mystery. If it's artificial, why haven't we found more like it? If it's natural, why does it mock the patterns we associate with design? One possibility is grim. Advanced civilizations might be tragically fleeting. They could flare into existence, broadcast for a brief cosmic moment, then vanish, leaving behind only fading echoes like this one. Imagine a universe littered with the ruins of empires that ascended too quickly, only to collapse under their own weight or succumb to unseen dangers. The echo might be the equivalent of a tombstone, a final signal from a species that burned itself out. But there's another, more unsettling angle. What if the silence isn't accidental but deliberate? The Great Filter hypothesis suggests some insurmountable barrier prevents civilizations from reaching interstellar maturity, whether environmental collapse, self-destructive technology, or something darker. If the echo is a warning, its careful timing and shifting patterns might be a cautionary tale, a way to say this far, no further without risking direct contact. Or worse, it could be bait. Some theorists argue that broadcasting might attract hostile entities, making stealth the only survival strategy for advanced life. In that case, the echo could be a relic from a civilization that learned too late the dangers of shouting into the void. Then again, maybe we're asking the wrong question. The Fermi paradox assumes aliens would think like us, seeking communication or expansion. But what if intelligence takes forms we can't recognize? The echo might not be a message at all, but the byproduct of a technology so advanced it blurs the line between nature and artifice. Picture a civilization that's merged with its own machines, its consciousness distributed across stars, leaving behind automated signals as naturally as trees drop leaves. To them, the echo could be mundane, a forgotten utility pulse, like an old power grid humming in an abandoned city. The chilling truth is this: the cosmic echo forces us to admit how little we know. After centuries of searching, the universe remains a hall of mirrors, reflecting back our assumptions in ways that unsettle as much as they illuminate. Every time that signal repeats, it's not just a mystery, it's a test of our creativity, our humility, and our willingness to confront the possibility that the answer to "are we alone?" might be far stranger than we ever imagined. The cosmic echo doesn't just pose a scientific riddle, it forces humanity to confront one of the most profound ethical dilemmas we've ever faced. If this signal is more than a quirk of nature, if it carries the fingerprints of intelligence, do we dare answer? The stakes couldn't be higher. On one side, the allure of cosmic kinship, the chance to finally know we're not alone. On the other, the terrifying possibility that reaching out could invite calamity. This isn't just theoretical, it's a crossroads where curiosity clashes with survival. History offers sobering parallels. When isolated civilizations made first contact on Earth, the results were often catastrophic for the less technologically advanced. The Aztecs mistook Cortés for a god, only to be decimated by disease and warfare. Could humanity now be the vulnerable party, blindly signaling into a universe where older, more powerful civilizations regard us as ants beneath their boots? Renowned physicist Stephen Hawking warned against this very scenario, comparing contact with advanced aliens to Native Americans encountering Columbus. It didn't turn out well. The echo's logarithmic precision suggests its senders, if they exist, operate on timescales and technological levels far beyond ours. What if our response triggers not conversation but conquest? Yet the counterargument burns just as brightly. To ignore the echo might be to reject our greatest opportunity for enlightenment. Imagine if the signal carries knowledge, a cure for disease, the secrets of clean energy, or even warnings about existential threats like asteroid impacts or gamma-ray bursts. The Arecibo message, humanity's 1974 radio broadcast to the stars, was criticized for potentially revealing our location. but its defenders argued that any civilization advanced enough to detect it would already know we're here. The same logic could apply to the echo. If its creators have technology to engineer such a precise signal across light years, they've likely spotted our industrial pollutants in the atmosphere or our TV broadcasts leaking into space. Our silence might be irrelevant. Beyond practical risks, there's a philosophical dimension. Responding would mark a conscious step into a cosmic community, fulfilling a yearning etched into our DNA. From cave paintings to the Voyager golden records, humans have always sought to declare, "We are here." The echo could be our first chance to join a conversation spanning the stars. But what if the universe is more dark forest than welcoming salon? Some theorists argue advanced civilizations stay silent to avoid predation, viewing any broadcast as reckless shouting in a jungle full of hidden predators. China's sci-fi epic The Three-Body Problem popularized this chilling idea. In a universe where trust is impossible, annihilation is the only safe response to a stranger's voice. The middle path might be caution without cowardice. Scientists like Jill Tarter of the SETI Institute advocate for active listening, decoding the echo's patterns exhaustively before transmitting anything. Messaging extraterrestrial intelligence, critics argue even this is too risky, proposing a global moratorium on replies until we understand more. But here's the twist. The echo's decade-long cycle means any response would take generations to reach its source, assuming we could even pinpoint one. This isn't a phone call, it's a message in a bottle tossed into an ocean light years wide. The real risk might not be attracting attention, but wasting centuries shouting into a void with no listener. Perhaps the most unsettling possibility isn't danger or futility, but irony. The echo could be a relic of a long-dead civilization, their final broadcast echoing eternally through an indifferent cosmos. Our response would then be less a handshake and more a eulogy, a tribute to beings who, like us, reached for the stars only to vanish before hearing a reply. In that case, the true ethical question shifts. Is it our duty to bear witness, to affirm that someone, somewhere, once mattered enough to say, "We existed"? The clock is ticking. Every 10 years, the echo repeats, its patterns shifting like a cosmic metronome. Whether we answer or stay silent, one thing is certain. The choice itself defines who we are, a species huddled in fear, or one brave enough to whisper back into the dark. From ghostly galaxies that vanish without a trace to black holes that refuse to play by gravity's rules, the Leo cluster is a cosmic hall of mirrors, one that keeps showing us reflections of a universe far stranger than we ever imagined. Think about it. We've encountered stars colder than the void itself, diamond planets forged in pulsar furnaces, and gravitational anomalies that laugh at Einstein's equations. We've listened to a pulsar's eerie song, chased phantom gamma ray bursts that leave no trace, and stared into void bubbles that might be wounds from a collision with another universe. Each of these 25 phenomena isn't just a puzzle, it's a key rattling the locks of our understanding, reminding us that the cosmos still holds secrets we've barely begun to name. What binds these mysteries together isn't just their strangeness, but their audacity. They don't whisper at the edges of science, they shout, demanding we rethink everything from the lifespan of stars to the very fabric of spacetime. The phantom galaxy taunts us with its disappearing act, the quantum ripple makes subatomic chaos visible on a galactic scale, and the lightless supernova proves even death can hide in the shadows. These aren't flukes, they're breadcrumbs leading us toward revolutions in physics we can't yet grasp. And that's the thrill of it all. Every unanswered question is an invitation to dig deeper, to stay hungry for the next revelation. So here's the real magic. You don't need a telescope to join the hunt. Every time we unravel one cosmic riddle, 3 more take its place, and that's where you come in. Maybe you'll spot a pattern everyone else missed, or spin a theory that cracks one of these cases wide open. The comments are your lab bench. Drop your wildest ideas, debate the possibilities, and let's turn speculation into discovery together. If this journey through the Leo cluster left you as awestruck as it left me, don't let the curiosity stop here. Hit subscribe to keep chasing the universe's boldest enigmas, from rogue planets to time-bending nebulae. Because the greatest lesson these 25 mysteries teach us, the universe isn't just bigger than we imagine, it's stranger, and the next mind-blowing revelation is always just one observation away. Ready for the next cosmic curveball? So am I. Let's find out what's hiding in the dark together.